Welcome friends to my channel. Now on yesterday's lecture, I have discussed about the moment of inertia of a thin rod, and then I took the example of a circular ring. Now in today's lecture, I shall going to discuss the moment of inertia of a circular disc. Okay, we all know, you also know it, that a disc is composed of a large number of rings. Okay, so let's proceed. Okay, so our next task is to find out the moment of inertia of a circular disc. Okay, so let us draw a circular disc. Okay, okay, now suppose the axis is AB. Okay, and the radius of the disc is R. Okay, so the axis is passing through the center and perpendicular to the plane of the disc. That is about an axis passing through the center and perpendicular to the plane of the disc. So the axis is this. Okay, about an axis passing through the center and perpendicular to the plane of the disc. So this disc is made up of large number of rings. Okay, so that's why we take an elementary ring at a distance x whose width is dx. That means this is dx. Okay, so if you look back to this picture, then here we consider an elementary ring at a distance x whose width is dx. Okay, okay, so one thing that I have to write, radius of disc is r. Okay, we take an elementary ring at a distance x of width dx. Okay, so what would be the area of this annular portion? Okay, this is x plus dx and this is x, so the area of the annular portion, okay, the area of the annular portion, the area of the annular portion, that is, the cross section is a circle, so we have to find out this portion. So that means this minus this, so the total is pi into x plus dx whole square minus pi x square. Okay, so this is the area of the annular portion, pi into x plus dx whole square minus pi x square. So if we simplify it, the result will be 2 pi x dx. Okay, so this is the area of the annular portion. Fine. Now 2 pi x dx. Now if rho is the mass per unit area, so if we consider rho is the mass per unit area, then what would be the mass of the elementary ring? Then the mass of the elementary ring is what? Mass of the elementary ring. Okay, the mass of the elementary ring will be, mass per unit area is rho, and our elementary area is 2 pi x dx. Fine. Okay, so what would be the moment of inertia of the elementary ring about the axis AB? If we call it di, so it is simply 2 pi rho x dx, mass into distance square, that means x square. Okay, so at first we find the mass of the ring, elementary ring, that is rho is the mass per unit area, and what is the area? 2 pi x dx. So this is the mass. So what would be the moment of inertia of the elementary ring about the axis AB? This is this. Okay, so this is 2 pi rho x cube, this is dx. Okay, 2 pi rho x cube dx. So what will be the moment of inertia of the entire disk about the axis of rotation AB? Simply we have to integrate this expression within the limits 0 to r, because r is the radius of the entire disk. So if we denote I is the moment of inertia of the entire disk, okay, so the result is 2 pi rho is constant, that is 0 to r. This is simply x cube dx. So if we do it, this is r to the power 4 by 4. Okay, so this is simply half pi r square rho into r square. Okay, so this is half pi r square rho into r square. Okay, half pi r square rho into r square, that can be written in this way. Now area of the disk is pi r square and rho is mass per unit area, that means pi r square rho is the total mass of the disk. Fine, so we can write this as half, oh, the marker is almost finished, so I have to buy a new one, sorry for that. So this is half m r square. Okay, so this is the result that we require to find out. Okay, half m r square. So the moment of inertia of a circular disk about an axis passing through the center and perpendicular to the plane of the disk is half m r square. Okay, fine. So this is the result. Now let us check what happens if we change the axis. Okay, simple. That is, if we take the diameter, about a diameter, if we take the diameter, so say this is one diameter and this is another diameter. Say this diameter is AB and this is CD. Okay. Now previously we calculated that half m r square is the moment of inertia about an axis passing through the center and perpendicular to this plane. That means about an axis which is perpendicular to this plane. That means moment of inertia about AB plus moment of inertia about CD, this equals to half m r square according to perpendicular axis theorem. And you also know that the moment of inertia is about the two axes are equal. Okay, equal because both are diameter, so moment of inertia will be same for symmetrical body. So if we take the moment of inertia about the diameter, AB is I, and that is same for the diameter CD, so I plus I, this we can write as half m r square. Okay, fine. So this is I, this is equal to 1/4 m r square. Fine. So this is the moment of inertia of the circular disc about a diameter, and if you can also write it ID, that means I diameter, or if you write I, no problem. Okay. So this is the moment of inertia of circular disc. Now you can also choose another axis that is about a tangent parallel to one diameter. Okay, about a tangent parallel to one diameter. Okay, so this is diameter and this is the tangent. Say this is AB diameter and this is the tangent CD. Okay, and this is suppose the radius R. So what we learned from parallel axis theorem, moment of inertia about this axis equals to moment of inertia about this axis plus a mass into r square. So we consider this as a tangent, so this tangent is parallel to the diameter AB. So if we call the moment of inertia of the tangent ICD, or you can also write I, no problem. So ICD, this is equals to IAB plus M into R square. Okay, so what is IAB? About a diameter, the result is 1/4 mr square, 1/4 mr square plus mr square, so the result is 5/4 mr square. Okay. Now these things you will find in Shenmukto Chatterjee's book. Okay, so this is the moment of inertia of different axes of a circular disc. Okay, now let us do a numerical regarding to circular disc. Okay, which is very important, and for question in exams this is also very important. The numerical is a circular disc of mass m and radius r. That means circular disc, given that the mass is m, the radius is r, okay, is set rolling on a table. Okay, so that means mass m and r radius circular disc is set to roll on a table. Okay, this set to roll on a table, this type of diagram. The marker is finished, so I have to buy a new one, so sorry for this. Okay, so this is the diagram. A circular disc is set to roll on a table, so we have to show that the total kinetic energy is, we have to show that the total kinetic energy is 3/4 m r square omega square. Okay, this is a very important question. Okay, Now in this case both energies are available, rotational kinetic energy and also translational kinetic energy. Why? Because it is said to roll on a table, that means translational motion is involved, and when it rolls it also rotates about its own axis, so there will be a rotational kinetic energy also. Okay, so what will be the result? Rotational kinetic energy we all know, half I omega square, and translational kinetic energy is what? Half mv square, that means half m, v means omega r, that means omega square r square. Okay, and what is I? What is moment of inertia of a circular disc about its own axis? That is half mr square. So we have to put half mr square. So this is half m r square omega square plus half m omega square r square. So this is 1/4 and this is 1/2, that means 3/4. We obtain the result. Okay, so this is a simple interesting problem. Only one thing, that at first you draw the picture. When you draw the picture, the it is clear to you that it is said to roll on a table, that means translational motion is involved, and while rolling there is some rotational motion about its own axis, so both kinetic energies are involved. Rotational kinetic energy half I omega square, translational kinetic energy half mv square. Just put v equal to omega r and here I equal to half mr square, because the moment of inertia of a circular disc about its own axis is half mr square. So after simplifying you will arrive at the result. Okay, so this is up to what today. If you don't subscribe my channel, kindly subscribe it to get latest videos on physics. Okay, thank you.